Hello. So now we are going to do our little review of sampling distributions. That is Barron's Unit 6 is really what this should say. In previous years, this has been listed under topic like 9 or 10, but it's the same stuff. It deals with sampling distribution. So I'm going to explain what a sampling distribution is, and then these are the types of problems you can see. Sampling distribution, the concept of it is the basis of statistical inference. And so what a sampling distribution is this. First of all, let's say you have a population. So let's pretend this circle represents our population, the whole group we want to know something about. Let's say it's every adult in Huntsville, Alabama. That's the whole group we want to know something about. And so we decide we want to estimate something. And so that parameter we're estimating, let's say is a mu. Let's say the mean weight, and let's say that's 180 pounds. Let's pretend that is the weight of all the 170,000 adults in Huntsville, Alabama. Okay, but we're estimating that. And so what we do is we take a sample. We get a subset, and we get, let's say we randomly select, I don't know, let's say 50 people. Certainly we want this to be at least 30, so we'll have normality, right? And so, and let's pretend, so we find the mean of those 50. And so it's probably going to be somewhere around 180. Okay, because we get a random sample and we don't have bias. Let's say it's 181.2. Okay, like that. And so now, but we say to ourselves, okay, this is just one of many X bars I could have gotten. If I took another sample of size 50, so like n sub 2, and found another X bar, 1 and 2, so I may get like 178.6. And if I took another sample, a third sample, and found a third X bar, I'd get another X bar. They're all probably going to be pretty close to 180. Okay, because we don't have bias. But if we took many samples and found many X bars, this family of X bars we refer to as a sampling distribution. That's what a sampling distribution is. It's every value a sample statistic could take in repeated sampling. And so whenever you get an X bar, you say, I've taken a sample and I found a sample mean. Here's mine. Is you say, but this is just one of many I could have gotten, and all the ones I could have gotten, we refer to as a sampling distribution. So a sampling distribution of X bar, of a mean of quantitative data, it will be approximately normal. So, and this is what is known as the central limit theorem. Our X bars will be approximately normal if our sample size is greater than or equal to 30, is our rough rule, or if it tells us the population varies approximately normally. Okay, so that's your little rule there. And the mean of the X bars will equal to the true value of mu, which in this case is 180. Then the standard deviation of the X bars is equal to our population standard deviation. So let's just pretend that that's like, I don't know, 5. And so this would be 5 over the square root of the sample size. And so, and that those formulas in essence are on your formula sheet where it says sampling distributions. Now, this is for proportions, which we'll talk about in a second, but for sampling distribution for means, the mean of the X bars is mu, and the standard deviation of the X bars is sigma over the square root of n. So that is a sampling distribution for a mean. That's the concept of it. All right, the concept for a proportion, let's say we're estimating some proportion. Let's say the proportion of people that are going to vote for a particular political candidate. Let's pretend that proportion is 0.45. We're estimating that. And so we took a sample of, let's say 200 in general proportion. Samples for proportions needed to be a little bit bigger. Of course, we had to get it randomly. So let's say that's our little subset. And we find the proportion in this sample that are say they're going to vote for the candidate. And let's pretend that that p hat is probably going to be around 45%, somewhere close to it, because we got a good random sample. And so we don't have bias. So let's pretend in our sample is like 0.47. But if we took another sample of size 200, and found another p hat sub 2. So it's going to vary from that just because of sampling variability. So maybe this one's 0.44. So what I say, and if we kept getting many p hats, we would create what is known as a sampling distribution for a proportion. And so here's our p, our true value, which is 0.45. The sampling distribution is every value p hat could possibly take in repeated sampling. If we took many samples, theoretically kind of an infinite number of samples, or just every possible sample, those p hats are the what we call a sampling distribution. So whenever you get a p hat, Whenever you take a sample and you get a p-hat, you have to envision this is just one of many I could have gotten. All the ones I could have gotten, we call that a sampling distribution. All right, and the mean of these p-hats, the mean of these p-hats, in the middle of the p-hats, will equal the true value as long as we don't have bias. And there's the formula for the standard deviation of the p-hats. It'd be the square root of p times 1 minus p over n. So, and this will be approximately normal. The p-hats will be approximately normal. If what is true, it's not sample size bigger than 30. Remember, it'd be approximately normal if n times p and n times 1 minus p are greater than or equal to 10. So that this is in essence the central limit theorem. So the central limit theorem says that your sampling distribution of x bars will be approximately normal if your sample size is bigger than 30, or if it says the population varies normally with that mean and that standard deviation, and a similar thing for proportions. Okay, so that's the theory behind all this. Now let's look at some problems, okay, in regards to the sampling distribution. And this theory is in essence the basis of how we come up with our numbers when we do statistical inference. In other words, when we make confidence intervals and do hypothesis tests. So this particular problem says the salaries of the workers in a city follow a very skewed distribution. Oh, with a mean of 70,000 and a standard deviation of 5,000. You randomly select 30. Now, by the central limit theorem, our sampling distribution will be approximately normal because our sample size is 30 or more, even though the population is skewed. Okay, but anyway, and you find the mean of their salaries. Describe the sampling distribution and the sample mean. Well, it is going to be every value x bar could take. Since we don't have bias and our true mean is 70,000, our x bars, our sample mean, that this is a mu, they are going to be around 70,000 and they will be approximately normal because of the central limit theorem. Now, by the way, if we had a small sample size, then our sampling distribution would start resembling the population distribution, the smaller the sample size. So if the sample size was like 10 or 5 or something, then our x bars would vary. They would vary skewed distribution. But the bigger it is, the closer it gets to normal. All right. And so and of course, when you describe a distribution, we have to cuss. All right. We have to cuss. And so you would say, well, the mean of the x bars, the mean of the x bars, that is this sample distribution for means will equal mu. And then the standard deviation that would describe spread is sigma over the square root of n. So the mean of the x bars is equal to mu. And that is, and so that is going to equal mu. And so that would be 70,000. Okay, like that. And then the standard deviation of the x bars, standard deviation of the x bars, that would be sigma sub x bar. That is equal to sigma over the square root of n. And so that is going to equal to 5,000 over the square root of 30. And that is about 912.87 or so. Okay. So the way we would describe it, the way we would cuss is you say, there's the center, there's the spread, and we'd say it's approximately normal. Of course, you'd write a paragraph here. So you'd say it's approximately normal with this mean and with that standard deviation. By saying it's approximately normal, that takes care of the unusual values too, because that's going to take care of the nature of the outliers as well. All right, so in number one, what's the probability the sample mean of the 30 workers is more than 71,000? So 71,000 is going to be somewhere up here, somewhere above it. So we're finding the probability of that or greater, 71,000. And so we'll do normal CDF. Normal CDF greater than 71,000. So that'd be 71,000 to infinity. Our mean is 70,000. And our standard deviation is 5,000 divided by the square root of 30. And so this would be our lower bound. That would be our upper bound. That is the mean of our x bars. That is the sigma of our x bars. And so let's see what we get. And so we go second vars, which is distribution, normal CDF, 71,000 to infinity. And then our mean is 70,000. And our standard deviation is 5,000 divided by the square root of 30. And we'll close parentheses on that. And so we get that is 0.136661 roughly. And so that would, in other words, it's a plausible thing. This is certainly above 0.05. So it could plausibly happen. So that's how you do that problem. By the way, if it had asked what's the probability of one worker being more than 71,000, you wouldn't be able to do that because we don't have normality. The central limit theorem doesn't kick in until the sample size is 30. So we had to have the sample size bigger than 30 because we didn't know the distribution, the population distribution was normal. But what if we raise our sample size from 30 to 80? So what's going to happen there? Well, what will happen there when your sample size gets bigger, it's going to make your standard deviation smaller. So your standard deviation of your X bars with 80 is now going to be 5,000 divided by the square root of 80. We're going to have less variability. So if you say 5,000 divided by the square root of 80, and so that is 559 about 559.017. Okay, so it means less variability. So let's see what this value is. What's the probability of the sample mean to be greater than 71,000? So this will be the same thing, except we're changing this to 80. So, and I won't write all that out, but we'll do normal CDF again. And so then we'll just change our sample size to 80. Okay, and so we get 0.03682. 0.03682, which is certainly less than 0.05. So that's a statistically significant result. And so why was your answer so much smaller here than there, even though the sample mean was the same thing? The sample mean was still 71,000. This didn't change. And what you need to realize is this: the bigger the sample size, it creates less variability. It's going to bunch together these X bars and create a smaller standard deviation. So the way you would explain this is this: the larger sample size creates less variability, a smaller standard deviation, less variability in the sampling distribution. So getting a value, a certain distance, in this case 1,000, 70,000 to 71,000, a certain distance from the mean is less likely. Okay, so so here in number 2, getting that value is plausible. In here, it's really not. It's less than 0.05. So that's one of the big important things about sampling distribution. The bigger the sample size, the less the variability. So that's a sampling distribution for me. Now let's check it out with proportions. All right, so it says 40% of residents in a city immigrated from Ireland. You randomly select 200 residents, calculate the proportion that immigrated from Ireland. Okay, so describe the sampling distribution of the sample proportion. Now, our population value is 40%. Okay, but we took a random sample and found the proportion. So it's probably going to be close to 40%, but not equal to it. Okay, because of sampling variability. All right, describe the sampling distribution of the sample proportion. All right, well, our true value of P is 0.4. So our P hats, our sample in repeated sampling, our P hats are going to be bunched around 0.4. Most of them are probably not going to be exactly equal to 0.4, most of them. They'll be bunched around, and that family of P hats we call a sampling distribution. All right, these P hats, if we're describing them, we have to cuss. We would say it's going to be approximately normal. Why? It's going to be approximately normal because N times P, which would be 200 times 0.4, and N times 1 minus P, 200 times 0.6. Well, that's going to be 80. That's going to be 120. They're both greater than or equal to 10. Okay, so approximate normal describes the shape and the nature of the outliers, with the mean of the P hats, the mu of the P hats is equal to P. And once again, that is on your formula sheet. So that is on your formula sheet. So the mean of the P hats is equal wait, I'm sorry. Yeah, the mean of the p-hats is equal to p. So that's that. And that's the standard deviation of the p-hats. So, and so that is equal to 0.4. Then the standard deviation of the p-hats would be the square root of p times 1 minus p over n, which n is 200. And that is about equal to 0.0. That's about 0.03464, about like that. And so that would be describing it like that. Okay, what's the probability the sample mean is 0.35 or less? Okay, well, in other words, 0.35, there's 0.4, 0.35 is somewhere down here. So there's 0.35. So we want this area, this curve, 0.35 or less. So we'll do normal CDF. So we have normal CDF. So, and that would be negative infinity to 0.35. Our mean is 0.4. Our standard deviation, square root of 0.4 times 0.6 over 200. Label this lower bound, upper bound, the mean of the p-hats, the sigma of the p-hats. And let's see what we get. So we shall say second bars, which is distribution, normal CDF, negative infinity, or you could just put negative 9 billion or something. And then our upper value is 0.35. And then the mean of the p-hats is 0.4. And then the standard deviation would be the square root 0.4 times 0.6 divided by 200, close parentheses. To get that 0.07446 about 0.07446. So not that big enough. It's pretty small. It's sort of unlikely, but it's not statistically significant. It's not below 0.05. And so in other words, it could plausibly happen. It wouldn't shock us if in our sample we got 35%, okay, in this case. But what happens when we increase our sample size from 200 to 400? We've doubled our sample size. What's the probability to get them? Now, once again, so what it's going to make your standard deviation smaller. Our standard deviation was this 0.034 something, but now the sigma of the p-hats is going to be the square root of, and it's still 0.4 times 0.6, but it's over 400. Well, let's see what that is. And so we'll say 0.4 times 0.6 divided by 400. Now it's 0.02449. So it's about 0.024495, let's say. And so it's less. It's less. And so there's lead, it scrunches together these p-hats. And so it's going to make it more unusual to go out in the same distance. So here, our sample value is 0.35. That's staying the same. Okay. But when we find the probability of that or less, all we have to do, and I'll just go up to this last command here. I'll just change this to our sample size to 400, right? And now our p-value is that. And so the answer to this question here, the answer to this question is 0.020613. Okay, now it's statistically significant. In other words, it really wouldn't plausibly happen with the sample size of 400, but it could plausibly happen with the sample size of 200 because smaller sample sizes have more variability in their answer. So why is this answer smaller? And you would say this, well, the larger sample size creates less variability. And let's use proper terminology here, please. Let's use proper terminology. Creates less variability in the sampling distribution. Sampling distribution. Okay, it scrunches together our p-hats, less variability in our sampling distribution. So getting a value like 0.35, getting a value a certain distance from the middle or the mean is less likely. It's considerably less likely, right? Here it's 7%, here it's 2%. That's considerably less. All right, very good. So that's sort of the main concept of a sampling distribution for a mean and proportion. Now we have a difference. I didn't put an example here for the difference in means. I'm just going to do a difference in proportion one. And because the difference in means is a very similar thing. You can certainly look in your Barron's book, or you can look at the sample and distribution videos we did, example videos we did earlier in the year, if you want to see one with means. But let's think about this. 64% of students at Smith High School are going to attend college. 51% of the students at Central High School are going to college. All right, you randomly select 200 students from Smith and 250 from Central and find whether or not they're going to college. So let me just jot this down. So it's Smith. So, and it tells us for all the students, it tells us the whole population value. That's the parameter. So P for Smith is 0.64. And then our sample size for Smith is 200, okay? Now for Central, all right, the proportion that are going to college, so P sub C for Central is 51%. And then the sample size for Central is going to be 250. So that's our information. It says, describe the sampling distribution of the difference in sample proportions. So Smith minus Central. So what we're estimating is the difference in proportion P sub S minus P sub C. Well, so the real true value, the true difference, as we say, if we call this the difference, okay, there's our true difference. It's 0.64 minus 0.51 is 0.13. Now you say, well, we already know the answer, so why are we estimating it? Well, this is setting up the theory that we're going to use in later chapters, in essence, to estimate the value. So we're in essence, so we know this, we're estimating that. So if we were to take sample proportions, all right, our P hat sub Smith for a sample size 200 and a P hat sub Central, we're expecting this to be 0.13. Okay, we would get a sample difference, but it's probably going to vary from that because of sampling variability. Okay, so here's let's look at all the possible differences. They're going to be centered around 0.13 because that's the true difference. Our sample difference, our D hat, if you will, is probably going to be close to that, but not exactly equal to it because of sampling variability. Then if we took more samples of size 200 and 250 and kept finding the difference many, many times, we would get all the possible differences. And so whenever we get our difference in samples, we say to ourselves, well, this is just one of many we could have gotten. These differences is what we call a sampling distribution of differences. All right. So that puts us here, a sampling distribution for proportions. Okay. The mean of these differences is going to equal the true difference. So, all right, well, first of all, they're going to be the differences. Let's describe the shape. They will be approximately normal, as long as n times p and n times 1 minus p are greater than 10 for both of these. And that's clearly true. 200 times that, and then 200 times 0.36, and 250 times that, 250 times 0.49. They're both greater than 10. So the shape is approximately normal. The mean of the differences is equal to the true value of 0.13. And then the standard deviation of the differences is this formula. And this relates to when we combine random variables, when we subtracted random variables and we'd have to add the variances, we'd square them and add them and take the square root. And that's what we're doing here. We're just taking this for both samples, squaring it, adding it, take the square root. So this would end up being the square root of, and we would say 0.64 times 1 minus that 0.36 over 200, and then plus 0.51 times 0.49 over 250, and let's see what we get. So we will take that and we'll say the square root of 0.64 times 0.36 divided by 200 plus 0.51 times 0.49 divided by 250, like that, and there it is. And so this value, the sigma of our differences, is going to be equal to, it's going to be equal to 0.04638534. Kind of like having a decent number of sig figs there to use in my calculation. So what's the probability, if we were to take these samples and find the difference, what's the probability our sample difference would be greater than 20%? 20% is somewhere up here. I don't know where, but somewhere above 0.3. So I want to find this area above 20%, above 0.2. So we shall do normal CDF. And from 0.2 to infinity, our mean is 0.13, and our standard deviation is all of that, 0.046385534. And so that's our lower bound, that's our upper bound, that is the mean of our differences. That is the sigma of our differences. I tend to use a shorthand version. This is the actual difference is p hats of 1 minus p hats of 2. So that's, anyway, that's, I think this is just fine. And so anyway, and so let's see what we get here. And so we will say second var's distribution, normal CDF, 0.2 to infinity. And then our mean is 0.13. And then our standard deviation is 0.04638534. That's plenty of sig figs, I would say. And so we get 0.06564 about. So above 0.05. So in other words, it is a plausible happening that would occur. We get a pretty decent amount of variability going on in our model. That's it. That is your quick little review of sampling distributions. Please send me any questions that you have, and I just hope you have a fantastic day.